Welcome back, my friends. Welcome back, welcome back, welcome back. Hey, we're going to take a look at kind of a qualitative point of view of bond length, which we've talked about. We did that when we looked at atomic radii. So if you look back at atomic properties and stuff, we talked about atomic radii. I would review that. That will help you with bond length. But I want to look at these three terms: bond order, bond length, and bond strength. And I want to focus on bond strength or bond energy. And we're going to do some quantitative calculations with that. But let's qualitatively look at it first, just based on the types of bonds. All right. So bond order, something I don't use very much specifically, but they like to say, hey, a single bond has a bond order of 1. That's one line. Double bond has a bond order of 2. It's got 2 lines. Triple bond has a bond order of 3 lines, or it's called BO, right? And you can actually use that to look at resonance structures. Like we looked at carbonate, which had the 3 equivalent Lewis structures. And so the true structure was a third of each. So each bond had the same length and the same energy in the laboratory. And we could represent that with a bond order of, say, 1.3, right? Or maybe halfway between, maybe you had a double bond and a single bond, two resonance structures equivalently. So the actual structure was halfway between a single and a double bond, or bond order of 1.5. So I guess it's useful when you're looking at equivalent Lewis structures and resonance structures, but I don't use BO bond order very much. Bond length, we've already looked at how to calculate those because we looked at the covalent radius. You can look up at a table. Remember how we determine the covalent radius? You take like hydrogen, chlorine, nitrogen, look at the distance between the 2 nuclei and divide it by 2. That gives you the atomic radius. And then you could take that and combine it with any other atom, get the bond, the whole length between the 2 nuclei. If you know one of the radii, you know the other one. So you can get the covalent radius for every single element out there. So bond length, technically, we've already learned, it's just the sum of the 2 radii. Take the 2 nuclei of the 2 atoms in the bond, take that atomic radius plus the other atomic radius, and you're good. So we've already explained this. I'm not going to go through it anymore. For example, if we did a carbon-bromine single bond, that bond length would just be the atomic radius of carbon, which you can go look up, and I found that as 77 picometers, and the covalent radius of the bromine atom, which I looked up, was 114 picometers. You add them together, you get 191 picometers. That should be the bond length of the distance between the nuclei of the carbon and the bromine. Right? Not too bad. And I want to look at, and I want to compare on the next video, well, what if you have different atoms? Or, well, it's pretty obvious if you have a bigger atom, right? So if you go down the periodic table, for example, remember atomic size gets bigger going down. So iodine's bigger than bromine. Everybody agree? So if I have the carbon-iodine bond, iodine has a bigger radius, so the bond length should be bigger. So the bigger the atoms, the further apart the nuclei are. I don't even think I need to write that down. That should be intuitively obvious. But what's not intuitively obvious at this point is single, double, and triple bonds, because that's a single bond. We never talked about double and triple bonds because we hadn't discussed those when we were talking about atomic properties. We haven't bonded anything yet. So let's do that on the next board. Let's look at single, double, triple bonds. Now, in relations between, you got BL for bond length and BS for bond strength. Okay, bond strength we'll find is it's correlated to bond length and bond order. They all overlap a little bit. But bond strength is how much energy. Let's say we had a laser and we shot it at a bond and tuned the energy. Maybe we hit it with energy, couldn't break the bond, and we just increased the energy of the laser until boop, right when that bond snaps in half. That's the bond strength, or bond energy is what they call it. A couple terms you'll run into. So how much energy does it take to sever a bond in half, right? Or vice versa, if you created a bond, how much energy would be released? It's the same number, just are you forming a bond or breaking a bond? I like to think in terms of breaking, which is dissociation. So a specific bond in a specific molecule would be the dissociation energy. But we're going to find out, and I'll spend a lot of time on this. What we tend to do is just, because there's so many different environments that a bond could be. You could have a carbon, hydrogen bond in methane or a carbon oxygen bond, CO bond in carbon dioxide with a carbon oxygen double bond. But you could have one in formaldehyde. You could have one in the carbonate. Well, actually, it's not quite a double bond in there. But you could have equivalent bonds in different types of molecules, which can adjust the bond strength a little bit. So bond energy is kind of an average over different kinds of species. So it's not super accurate. The bond dissociation energy is a little more accurate. It's a specific one, but it'd be really hard to track all of those, okay? Every type of bond and every type of molecule. Forget that one. So I'll show you what bond energy is, and there's tables of that. So you've got BO, BL, and BS, or BO, bull, and BS. Just got to entertain yourself. So let's look at a qualitative relation between these three, and then we'll spend some quantitative time doing this. We did this quantitatively in the atom size video, so I think we're good there. All right, here's our qualitative comparison. Let's do bond order, bond strength, and bond length. All right, now remember, bond order, a single bond would be 1, double bond would be 2, triple bond would be 3. And we'll just use carbon-carbon bonds as an example. So carbon-carbon single bond order of 1, carbon-carbon double bond order of 2, carbon-carbon triple bond order of 3. Yeah, not too tough. But let's look at the trends. No numbers. We'll do quantitative next. Let's qualitatively look at, well, which of these would have the highest bond strength and which of these would have the greatest bond length, right? Or we'll rank them from, say, weakest to strongest, which takes the least amount of energy to break, which takes the most amount of energy to break. And then bond length, which is the shortest, which is the longest. Oh, okay, well, let's think about it. I don't know if you ever played that game, Red Rover, when you were a kid, right? We used to play it all the time because when I was a kid, we didn't have video games. We didn't have color TV. We only had like 4 stations. We had channel 2, 4, 5, 7, 9, and 11. So I think might have had 13, I can't remember. So 6 or 7 channels, right? No remote control. So we didn't have a lot of time. Nothing to do inside, right? So we just go outside and knock on doors till you found some friends to play. So let's play. If you could get enough people, you could play Red Rover where you'd get one person standing away from everybody else and the rest of the people would form a line and join arms, right? They join arms. And then the one person who's separate have to kind of scan through and go, who looks like the weakest? And I'm going to sprint through and try to break through their arms, right? And you try to snap their arm. Well, not break their arms, but try to, break their grip. It was a lot of fun. And you'd be like, oh, I failed. Then you'd have to pick somebody else. Just things you do outside, right? Freezing my butt off in Minnesota. Now imagine if I'm just holding one other person's arm, right? So you're just connected like this, like a single bond. Electron is one hand, electron's the other hand, and they clasp. Trying to break through 2 people holding hands, if you run fast enough, you might be able to snap it. But imagine if those 2 people clasp both arms. So they take this arm and clasp, and then the other one in class. This is easier when I have another person in lecture. Bring somebody up and do it. But you'd have to break through 2 sets of arms like a double bond. Breaking through 1 set of arms is one thing. Breaking through 2 sets of arms, if I had someone else I was holding their hands like this, good luck breaking through that. And what if you could have 3 sets? Would you agree it's harder to break through that? So the more electrons that are shared between atoms, the stronger that bond, the more energy it takes to break it. So the way this works out is this is the weakest bond, right? Easier to run through, people just holding hands. But if they're holding both sets of hands, it gets harder. So this would be the strongest or the highest bond energy or bond strength. See that? Boom. Now let's think of it the other way. What if you've got 2 people holding hands, just one, right? So I'm just grabbing their hand like this. Their bodies are pretty far apart. So think of their bodies as the nuclei, and they extend their arms up and grab hands. That's a long distance between them. But if I wanted to grab their other arm, I'd have to pull my body in closer to grab it. So if it's just one, I'm way over here. If I grab their other one, boom, it pulls their bodies closer together if they grab both of their hands. Do you see that? So when you go from a single bond to a double bond, the more electrons, doesn't make sense, there's more electrons, pulls the nuclei in closer together. And if you had a triple bond, it pulls them in even closer. So the more electrons you're sharing, the shorter it gets. Okay? So this is the longest bond. And the triple bond is the shortest bond. So bond strength and bond length are opposites. Now bond order, right, and bond strength go together, right? The higher the bond order, the stronger or higher the bond energy, but the opposite's true of length. So again, the more electrons shared between two atoms, the stronger the bond, and the closer it pulls them in, the shorter the bond. Let's put some numbers to bond strength. Let's do it. We're going to calculate this stuff and do some cool things. There's two ways we're going to look at bond energy, okay? We're going to look at the first one, bond dissociation energy, like I defined, and the other one, and then just bond energy. Now, one's a little more useful than the other. Let's take a look. So D, or dissociation, usually people just call it dissociation, or to break apart. It's the energy required to break apart, exactly by definition, 1 mole of a specific type of covalent bond. Maybe it's a bromine-bromine bond, or whatever. Typically, this is applied to diatomic molecules, H2, N2, Cl2, Br2, I2, in the gas phase, though. Right? This is in the gas phase, so we can think of it almost theoretically for certain species. So let's say we got chlorine gas. Well, it's diatomic. If we break that bond, we get 2 chlorine atoms. An easier way to look at it is to draw the diatomic molecule, right? I didn't put the lone pairs on there if we wanted to complete the octets. But let's say we sever that bond. You can use a laser, whatever it works. Sunlight does it, right? Chlorine gas doesn't exist in the atmosphere because the bond's too weak. Right? So sunlight in the visible region is enough to break that. That's why it's colored. It's green. I did it in green there. So we break that into its separate chlorines. Well, how much energy does that take? Well, that takes specifically 243 kilojoules for every mole. So if I had 2 moles, I would just double it. If I had 3 moles, I'd triple it. Right? So this is a conversion factor between the amount of that substance, the number of bonds, and the energy in kilojoules. Back in the old days, we would use kilocalories. Right? That's okay for mostly diatomic species. So we'll put diatomic molecules where the bond is very specific. But what if we're looking at something like methane, CH4? You got the carbon-hydrogen bond. But I could have a carbon-hydrogen bond in other species other than methane. I could have one in ethanol, right? I could have one in, CH2S, right? So there's different types of molecules I could have that specific type of bond in, and it turns out the energy, the dissociation energy is different in those different molecules for the same bond. Oh no! So this concept, dissociation energy, kind of falls apart when you're looking at molecules. So that's where we're going to get another term called the bond energy, or average bond energy. We're going to average that specific carbon-hydrogen bond, say, over many, many different molecules. So maybe it's, 143 picometers in that one, and 148 picometers in that one, and 172 in that one. We just average them. That's what we tend to use. Not real specific. It doesn't give you real accurate values, but it's useful because it's too hard to track otherwise. So let's look at that. Right, this will kind of show you the conundrum we run into. What if we're dealing with not diatomic molecules now, where it's pretty straightforward what that bond dissociation energy is? What if we're dealing with molecules? That same bond, like I said, can occur in many different molecular environments. So for example, we got methane here. Let's look at the carbon-hydrogen bond in methane. Let's call that D1, the dissociation energy for that. But now let's look at this particular species. Think of this formaldehyde, right? So now instead of CH4, you've got a double bond to an oxygen, hydrogen, hydrogen. So taking that carbon-hydrogen bond, that might have a different dissociation energy than this one. And what if we take like a chlorofluorocarbon? We got 2 chlorines and a fluorine, that carbon-hydrogen bond. That's a totally different molecular environment with a different dissociation energy. Let's call that D3. Same bond, different dissociation energies. So if I said, what's the bond energy for carbon-hydrogen? You're like, I don't know, which molecule? So we have to take a situation and go, well, it's going to be too difficult to do it for every single known molecule. Let's just say, on average, if we take D1 plus D2 plus D3 plus many, many other molecules a carbon-hydrogen bond would be in, and average those, right? This is just a rough example. We'll call that the bond energy, or the average bond energy. We'll call that BE. So BE is different than D. D is a specific dissociation energy for a specific bond in a specific molecule. Bond energy takes that same bond in many different molecular environments and averages the D values. So it's way less accurate. all right? But it gives us a simplistic way to look at things. So there's tables of bond energies. I typed one up for you, some values I found. Bond energies, and these are averages, right? So nitrogen, now the triple bond between that's probably probably the same as dissociation energy. Same with the chlorine-chlorine bonds and bromine-bromine bonds, right? Because these probably come from the diatomic molecules, right? So the D in that case is equal to Be, but a lot of these other ones, right? So here's the hydrogen-carbon. On average, it's about 414 kilojoules per mole, right? If you average over all the different types of situations it can be in. So this is something I would provide for you. There's an exception on the bottom for carbon dioxide. We can get a carbon-oxygen double bond pretty specifically. See that little star there? Where'd that star go? So carbon-oxygen double bond, right? So in carbon dioxide, it's about 799 kilojoules per mole. But if you take all the different scenarios where carbon-oxygen can double bond, it's about 736, like here, right? That's not going to be 799. Again, averages. What can we use these for? We can use these average bond energies to actually calculate the change in energy for an overall reaction. Not super accurately, but it can give us a rough idea of, hey, if this chemical reaction occurs, does it require energy? Is it endothermic? Does it go downhill? Does it release energy? Is it exothermic? Roughly what value, how much energy would be released or absorbed for that reaction to occur? So it gives us a rough estimate. When we get to thermodynamics, that will give us a more specific way of calculating it. This is just kind of approximate. It's around this kind of value. So let's show you how to do that. Use bond energy values to calculate energy changes for entire chemical reactions. Let's do a little theoretical thought game, okay? So if we have a chemical reaction and we want to kind of roughly estimate the overall energy change that occurs for that chemical reaction, we can use bond energies for that. The way we're going to do it does not, note this, it is not representing how it actually happens, okay? This is just a thought process. Let's calculate the overall energy change. Let's call that the heat of reaction. We'll find out that's an enthalpy later. Delta, that delta means change. So that's effectively the change in the energy of the reaction or the heat released or gained. And you may remember the terms exothermic means heat's released and endothermic means heat's absorbed. So an endothermic reaction requires energy through heat to go, whereas an exothermic one just spontaneously can occur releasing heat. All right, we'll do that more when we get to thermodynamics. So here's our theoretical process, right? Let's draw the Lewis structures for all of our reactants. And let's go pew, 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 and break every single bond, right? Every single bond in all the reactants, we're going to break them all and then atomize everything. So it's all in the gas phase. So now all the individual atoms are floating around in the gas phase. We broke all of those bonds, which requires energy, right? That's endothermic. So that will be a positive, if I can spell right, a positive value. Breaking all of the bonds requires energy. It's endothermic. It's going to be a positive value. And if we knew all the bond energies, we could calculate that. It might be, we might have 20 different bonds, so we'd have to do 20, or it could take forever, but it's doable, right? Theoretically. And then we'll take all of it. It's like taking a big Lego thing that my son makes and go smash into all the individual Legos. And then we can re-put them together and make something different, right? So if we take all those atoms in the gas phase and now recreate all of the bonds to form the products, well, that would be the opposite. That would release energy. Breaking a bond requires energy. Forming that same bond releases the exact same energy. So to sever a nitrogen-hydrogen bond would require 389 kilojoules per mole. When we form it, it would release 389 kilojoules per mole, or be negative. Oh, that's exothermic. So forming the bonds is a negative value. Breaking the bonds is positive. So break the reactant bonds, form the product bonds. So would it make sense if we summed all the bond energies of the reactants and subtracted all the bond energies of the products? That would be the overall energy change. Not super accurate because these bond energy values aren't super accurate, so it's an estimate. And it really will kind of tell us, hey, if we get an overall value that's positive, that tells you it's an endothermic reaction. If you get an overall value that's negative, it's an exothermic reaction. And the value would be a rough estimate, but I mean, it could be 10, 20, 30% off at least, right? So let's show you what that all means. So here's the limitations of what we can do with this. So, I mean, you can see an equation would form from this, right? So the overall energy change of a reaction, called the heat of reaction or enthalpy of reaction, we'll define that more in thermodynamics, was approximately, we could put equals, but remember, we're using average bond energy values. The total sum of all the bond energies of every bond of all the reactants. So you have to count for the stoichiometric coefficients, the number of bonds in the molecules we'll go through, minus all of the bonds formed in the product. So the sum of all of that, right? Because breaking bonds is a positive value, forming bonds is a negative value. So you just use the values on here, add up all the reactants, subtract all the products, bonds. Hey, got to get your Lewis structures right. So again, this provides a rough estimate of the overall energy change or heat of reaction or enthalpy of reaction. But it does give us a fairly decent chance at predicting whether reaction's going to require energy to go, which is endothermic, or release energy, which is exothermic. So if the delta H reaction is positive, it means we have to put energy in. It has to absorb energy from the surrounding environment via a Bunsen burner flame, a laser, voltage, whatever. We need to put some energy in to make that reaction occur because it's not favorable, right? But if delta H reaction overall is negative, that means it's a favorable process. That's probably going to happen on its own. There's other factors, entropy and stuff we'll look at later. But that's exothermic, and that will release heat. So to you, if you did a reaction and it felt hot, you ever do that where you mix things in a test tube, you go, whoa, that's hot. That's an exothermic reaction, releasing energy to the surroundings, you being part of the surroundings. Let's do an example, show you how to set this up. Let's make it happen. You ready? Let's estimate the heat of reaction or enthalpy of reaction, and we can say whether it's endo or exothermic. Using bond energies, we're going to do it more accurately with thermodynamic principles later. Let's say we have nitrogen trifluoride in the gas phase, reacting with diatomic oxygen gas, giving us nitrogen monoxide gas, nitric oxide, and diatomic fluorine gas. So we got 2 NF3s, 1 mole of O2, 2 moles of NO, and 3 moles of F2. So you have to count for the coefficients. So you have to draw the Lewis structures first. All right? So first, to draw Lewis structures. Now, why I find a lot of students try to skip the Lewis structures and then they miss the fact that there might be a double bond there. Right? They're like, oh man, I did a single bond, right? I did a carbon-oxygen single bond, but I was supposed to do a carbon-oxygen double bond, and those are different, 360 versus 736. You're going to be way off on your answer, so you got to do Lewis structures first. So I want you to pause this video, do all your 6n plus 2 minus number of valence electrons for these. These should all be easy except NO, which I did for you when we did free radicals. That you're going to get a 6n plus 2 minus valence electrons of a plus 3, which means you have a double bond and an electron deficient atom with 7 electrons on it, which is the nitrogen. Go ahead and draw those. I'm going to pause mine, and you don't need to watch me do them all. I'm going to draw my Lewis structures, and that way we can count the number of each type of bond in the reactants and products. And if you're in my class, you can download my bond energy table, right, either to your phone or print it out. Go for it. This is what your Lewis structures look like. So NF3 probably got a 6n plus 2 minus valence electrons of 0. So we've got the single bonds there, complete the octets. Oxygen's diatomic. The nitric oxide, right? You got the free radical on the nitrogen there with the double bond. And then the diatomic fluorine. Remember, you got 2 of those, 1 of those, 2 of those, and 3 of those. So let's count up the number of bonds, right? You ready? You ready? You ready? Do you see that one molecule of NF3 has 3 NF single bonds, right? Well, what if we had 1 mole? That would give us 1 mole of 1 mole of NF3 would have 3 moles of NF single bonds. But how many moles do I have? 2. So if 1 mole of NF has 3 NF single bonds, 2 moles would have 2 times 3 or 6, right? So let's go 6 moles, right? 1, 2, 3, do it twice, 4, 5, 6. There's a 1 in front of that, so that's it. So this, we have 1 mole of oxygen-oxygen double bond. What's over? Oh, this is a 2, isn't it? So 1 mole of this has 1 mole of nitrogen-oxygen double bond, but there's 2 moles. So this is 2 moles of nitrogen-oxygen double bonds. And we can find those values on the table. Over here, the fluorine, diatomic fluorine, 1 mole of that has 1 mole of single bonds, but we have 3 moles of it. So there's 3 moles of fluorine single bonds. Now, I don't normally write that down. I just do that in my head, okay? So we're just going to take 6 times the NF value plus 1 times the OO double bond value minus 2 times the NO double bond value minus 3 times the FF single bond value. Whoa, let's do it. I'm out of space. I've seen several different ways to set these up. Not too particular about it, but I do like to keep track of things. So there's our equation. So the overall enthalpy or heat change of the reaction is the sum of the bond energies for all the reactants minus the sum of all the bond energies for all the products. So I've seen people just do them all individually, put positive values for the reactants, negative values for the products, and just add them all together. That's great. This makes it, a little bit quicker, I think. So remember, we had 6 moles of, if you look at the Lewis structures, we had 6 moles of the NF bonds, correct? So we're going to multiply that by the bond energy in kilojoules per mole. We'll look that up. We had 1 mole of oxygen-oxygen double bond. So let's look up the kilojoules per mole for the oxygen-oxygen double bond. That's in brackets, that's the sum of all the bond energies of all my reactants. And then I'm going to subtract from that the sum of all the product values, right? Which releases energy. That's why the negative sign's there. So we had 2 moles of NO double bonds. Let's find that, kilojoules per mole. And 3 moles of fluorine single bonds. Let's look that one up. Now, this table is nowhere complete, so if something's not on the table, I will provide you that. I'm not going to write everything on there. I'll provide you that on a quiz or exam where you can look it up or something like that. So actually, I found 3 of these 4. Let's look up nitrogen-fluorine bonds. Now, do you see nitrogen? There's nitrogen-hydrogen, nitrogen-nitrogen, nitrogen-oxygen. Well, poopy darns, man. There's no nitrogen-fluorine. That's when you go, oh, teacher. It's in the I would give that to you. So I poked around. I saw several different values, right? That's why these aren't accurate, ranging from like 272 to 283-ish range. Most common one I saw was 272. So let's use 272 kilojoules per mole for the nitrogen-fluorine single covalent bonds. I would provide that value to you, right? But usually on an exam, you'll find all of these. Let's look up the oxygen-oxygen double bond. Do you see oxygen-oxygen double bond on there? Is that it right there? 498 kilojoules per mole. So let's write 498 there. Biggest mistake students make on the exam, they don't do the Lewis structure, and they end up using 142, thinking it was an oxygen-oxygen single bond. Nope. Let's look up nitrogen-oxygen double bond. This is kind of an average value. Hopefully that's on there. You see it right there? Not nitrogen-oxygen single. That's 222. We want nitrogen-oxygen double bond, which is 590. And I'm going to put a decimal point there. These should be good to the ones place. These are averages, right? So 590. But I'm going to put a decimal there just to say these are good to the ones place. All right? And then fluorine single bonds. This should actually be a pretty accurate one because fluorine's diatomic. See the 159 right there? So let's go 159 for fluorine. So what I want you to do is take 6 times 272 plus 1 times 498. Write that value there. And then take 2 times 590 plus 3 times 159 and write that number there. Tracking, not great. I mean, these are pretty uncertain values. So these are exact numbers, these 2s and stuff. So really, it's an addition. You're doing 272 plus 272 plus 272 plus 272, right? This is really an addition type problem. So we're going to be limited to the ones place. So do those values. I'm going to pause this, calculate this myself. Let's see if we get the same numbers in there, and then just subtract them, and we'll be good to the ones place. Let's see if we get the same thing. Assuming I hit the buttons in my trusty dusty calculator correctly, I did 6 times 272 plus 498. I got 2,130 kilojoules. Good to the ones place, so I put that naked decimal there. Although sig figs aren't a huge issue here, they're approximates anyway. I took 2 times 590 plus 3 times 159. I got 1,657. So it takes 2,130 kilojoules to break all of those reactant bonds. It releases 1,657 kilojoules when you form all of the product bonds. So breaking the reactant bonds, forming the product bonds. Obviously, it's releasing less than it's taking in, so it requires more energy than it releases. So we're going to end up with a positive value. Obviously, if this is bigger than that, you'd get a negative one. So the net result is I get 473 kilojoules. That's the change, right? Since that's positive, that would be an endothermic reaction. Now, that's not going to be a very accurate value. But it's definitely, we could say this is going to require energy. This would not be a favorable process. Boom! You got it. Another way you could do it, see how you end up with kilojoules? You could also say kilojoules per mole of reaction. You'll hear that a lot. You could also, you'll see this as kilojoules, because moles cancels out. Sometimes you'll see kilojoules per mole of reaction. We'll hit that more in thermo. We did it!